I think we should keep it as is. Yeah. Please go ahead. Please go ahead.
Okay. So I'm nice to meet you, everybody. And I am Jean-Paul Chaput, and I am the lead architect of the Coriolis toolchain, which is the RTL to GDSII toolchain. So I will present the outline of that toolchain in this presentation. So I will start to present what is a layout, how to make an ASIC, and then finish by a little demo. So the first thing, just a bit political to start, is why are we doing Coriolis? So in the last years, there was a big trend about open hardware. But open hardware stops at the RTL level, that is the logical description of your component or your ASIC. What we want to achieve with Open EDA is allow you to go down to the silicon. That is really make the chip all the way down. So that's our main goal. Obviously, it has also some interest for the academics, in the sense that the way ASICs are done today, they cannot share, academics cannot neither share their design nor tweak the tools. You have to use the commercial tools and you have to use them as they are, and you cannot change them. So in that regard, Coriolis is a big progress in the sense that if the algorithm didn't fit your needs, or you want to make some very special tweak, you can do it. Of course, it also gives you the ability to publish, share, and modify the hardware design, like it's the idea very close to the GPL and the free software. This is why it's a FOSS toolchain. And beyond that, what we want to achieve is to build a community. So people can share their design. You can not only tweak the tool, but you can also share your design and start to build a community and not reinvent the wheel in each company. We also want to open the market to SMEs, because today only very big companies can afford the price of the tools to make ASICs. Another point is the security issues. Something people are not often very much aware is that you cannot have software security unless you have secure hardware. It is easy to introduce hardware Trojan inside the design and at hardware level, and it will be absolutely impossible to suppress, and it's a danger. When you have fabless companies, they want to ensure that the design they send to the foundry or to the factory that make chips, that what they get back is exactly what they send, and not some slightly modified design. And one last point is that in some occasions, you need the hardware for a very long period of time. You can take the first example that comes to mind, especially when you are in France, is the nuclear power plants. Nuclear power plants have been qualified for a certain type of hardware and ASICs, and to stay qualified as operational, you need to have this hardware along during the lifetime, the whole lifetime of your plant. That means 50 to 60 years. And having one chip available for 60 years, I don't know even of one of them now. So that's potentially a problem. So that's what we want to do. About now an ASIC, I am assuming that some of you are not familiar with what is making an ASIC. So the first point of making an ASIC is basically an ASIC. What is it? You send it what you send to the factory is a layout, a big drawing. A layout is basically a big drawing,
But of course, a very complex one. The one I display here is a very, very old one, back from the 80s. The point is that it's not too small so that you can still see the parts. But nowadays, they are so small, the rectangle, the drawing are so small that you barely can see anything. But anyway, the point is that it's just a drawing, but a drawing that obeys a vast amount of rules. This is not any drawing, and it is basically a map. So, back to the design flow, and what I want to illustrate here is to, for people who are most familiar with the FPGA design flow, because FPGA is much more affordable, and many people are working on FPGA, especially in open hardware. On the left side, you have the classical design flow for FPGA. I take it an open design flow, a FOSS design flow, with you have as a first step the logical synthesis, usually performed by Yosys. Then you perform a place and route on the FPGA matrix with a tool like NextPNR or VTR. That tool in the end generates a bit stream that you send to the FPGA, and it is used to configure the material component of the FPGA. That is the communication matrix and the LUTs. But an FPGA is a kind of specialized ASIC. On the right side, you have the first step is almost the same. That is, it's a logical synthesis, but on a different target. It's not targeting FPGA, it's targeting the standard cell library. You get a netlist, and then you perform the physical synthesis. The physical synthesis is the task of making the mask. At this stage here, you have the layout, the famous layout, and then you send your layout to the foundry. And the foundry is the factory which is tasked to build your chip. Typically, this is TSMC. I'm sure you are aware of the weight and the importance of TSMC in Taiwan. So, in the right toolchain, we have currently two roadblocks. The first one is the foundry. Because the foundry impose NDA, non-disclosure agreement, to protect its technology. Because that layout is very informative about how you do things and how your technology works. So, in order to protect their secrets, most of the foundry impose NDA. That is, you cannot share your design. You can only transmit your design, your layout, to the foundry tasked to build it. The second roadblock is at the level of the EDA tool. The EDA tools are very costly. Because the design are usually costly, if you make a chip, it's costly, then you can afford costly EDA tools. For example, I think for one of the main provider, which is the main company, which is Cadence, one license is 100,000 euros per year. So it's okay for big companies like Apple, IBM, and others, but for SMEs, it's completely out of the question, and for individual, even more so. So what we are tackling here is that we are tackling the EDA tool problem. We will see also that the NDA problem has started to be broken by Google, which is providing for free a technology which is the Skywater 180 nanometer, and Global Foundries has started to do the same with the 180 nanometer technology. So this roadblock is starting to crumble, and we had to do the same here, because to lower the price here, if the price lowers here, we need to lower the price here too, and also give freedom. So now let's have a small detour about the standard cell library. So it's kind of a zoom on a part of the flow. So you still see the logical synthesis part. The point of the logical synthesis is to break your design. Here it's the RTL version of your design, which means the logical description of your design. It's basically a big set of Boolean equations. So you break your Boolean equations into small bits, which are the standard cell. Basically, it's small bits of logic. You have NAND gates, NOR gate, and flip-flops. I mean, okay, you have much more than that in terms of gate, but basically, it's an atomic Boolean function and memories, small memories, 1-bit memories. So you break that into the standard cell library. The point of the standard cell library is that it has an equivalent in terms of layout. So each bit that you have on the left side can be replaced by a bit on the right side, which is its equivalent in silicon, the drawing in silicon, that can perform that function. And then you reassemble them to build your whole layout. And this is the task of the 2 steps here, place, then route. We will go into those 2 steps deeper in the following slides. So, but the point is that the pivotal point is the standard cell library. So we need standard cell library to make our designs. And moreover, it's the layout which is interesting us. That is the drawing, the atomic drawing of it. So let's dig a bit deeper in the layouts. You have on the right side the direct way to do it. That is, you have rules to make your layout, your drawing, rules which are expressed in micrometer or nanometer, and then you draw your library. But the problem is that every time you change of technology, of target technology, say you want to go from an AMS 180 nanometer node to a TSMC 180 nanometer node, then you have to redraw all your standard cells. So a standard cell library can contain between 100 gates and maybe 1,000 gates in the case of the latest one. So that's quite a lot of work. And in the 80s, 2 American professors make an observation. It was Mead and Conway in the 80s. They are quite famous for that. They make the observation that the technology are not so different. Meaning, if you have a technology in maybe 1 micron, and you go down to 500 nanometer, then finally what you do is mostly perform a shrinking. All the technology are almost the same, but they are just, the difference between them is just a scaling factor. So what they said, instead of drawing our layout directly in the target dimension, we use an anonymous dimension. This is the lambda. It's called the lambda. You draw all your lambda, and then you perform just a translation saying that, okay, my target is 180 nanometer, then 1 lambda equal 180 nanometer. Of course, it's a bit complex. It's a bit more complex to compute the value of the lambda, but basically this is what we do. And we can translate our library almost automatically to any target. So this is, so we have another approach which was developed by PDK Master from Staff Verhagen, we'll talk about it a bit later, which is use stick diagrams instead of true rectangle, and then he used another program which flesh out the stick diagrams and give the sticks the right size. So that's another approach. So basically what we can do with symbolic layout is that you have your symbolic layout, and then through a simple tool which is called S2R, symbolic to real, you can project your design to any technology. You can have AMS, TSMC, those 2 are under NDA, but you can also use the one which are not NDA now, which are Global Foundries 180 or Skywater 130 nanometers. So this is the point of symbolic layout. Another advantage that was not foreseen at the time is that those layouts, the symbolic layout is free of NDA, as it is not related to any specific technological node. It is not under NDA. and you can share that design. So for people to see what you have done. And people can even use that layout to compare with the real one, because the differences are not so big. And if you want to see some transistor or Trojans or hardware Trojan had been added, you can see it by comparing the two layouts, because they are not so different. Unfortunately, this approach, this symbolic approach, is no longer working for deeper node because of a difference of the shrinking rate between the active area, meaning the transistors, and the wiring, that is the metal wire that connect the standard cell between them. So we have developed some hybrid approach. That is what Coriolis can manage is those four approaches. It can manage a wide range of mix between symbolic layout and completely real layout. So on the left side, you have the most symbolic one. Each arrow here means a symbolic to real translation. So here we have a symbolic to real translation. Here we have one, and here we have one. So we have the first approach, which is the true symbolic, which means you translate your whole design, your standard cells, and your wires. Everything in one go is translated. This approach is no longer working well, at least, for a deeper node. But what we started to implement is that we only translate the standard cell library, and then we draw the wire with real wires. We do the same with PDK master, but the difference is that the process, the S2R process, is different between the two. The processes are different to get better result. I mean, we don't know yet which one is giving the better result in terms of fitting the technology. And lastly, Coriolis can also manage fully real layout. So end-to-end real, you use real cells and you generate a real design. So it's a feature which is not often, it's often overlooked, but it's very important, and it gives Coriolis a lot of flexibility about what he does. So let's get back to the whole design flow. So I'd say whole design flow, but it's still a simplified version. For example, here, the little box validation is a lot of tools, in fact. It's a complex things. But the idea is to give you an outline. So you have the cell library here, which is used by the logical synthesis and the physical synthesis. When I said that Coriolis is a whole design flow, it is a bit of a lie, in the sense that we only provide the blue part. So the standard cell library, in some case, and mostly the physical synthesis step, because this is a huge work to provide all the bits. And what we provide is integration. Coriolis provides a way to integrate all those steps through a Python script based on do it. So to simplify and to be more the marketing message, we just say it's Coriolis, it's simpler for people. But we are using other tools like GHDL, which is a VHDL simulator to check your design and simulate your design. We can take any design coming from those HDL generator. So NMiGen is now Amaranth, mostly. You have also Chisel, Spinal HDL, which is a variant of Chisel. Yeah. And then you get your RTL. Then you get just logical synthesis. After the logical synthesis, you check that your design is still good by comparing the results of the simulation of the two. Here, you have also a GHDL validation, but not only. You have a step like DRC on LVX, when you check that your layout itself is correct, and you check that the netlist that you got is the same as the one you want. And finally, you get the symbolic to real translation. And then you can, under NDA, perform some validation with layout. Is the DRC, another DRC. Okay. This is the variant of the design flow when you are using the real layout directly. In that case, the S2R step disappears and you go straight to the real layout and then the validation through layout. And of course, you cannot distribute the cell library. The cell library is under NDA. This is no longer true for the liberated technology like the Skywater and the Global Foundries 180. So, what does placement mean? As I said, when you perform, when you have we are after the logical synthesis step. So we have broken down you have broken down your design into gates, and you can replace those gates by their equivalent in terms of layout, which are represented here. And usually you have to place them inside a square area. But you don't place them like just at random or with completely arbitrary rules. In fact, you put them in rows, and rows are stacked on top of each other. Moreover, the rows are which have different orientation, because here you see that you have usually power lines on top and on the bottom of the standard cell. So VSS, the ground, on the bottom, and the power line, VDD, on the top. In order to share the power lines between rows, you have to flip them over, one row over two. And so you see that we have, so in the Y coordinate, in the vertical coordinate, you have to respect a certain slice, so they are pitched, and it's the same horizontally, but it's a smaller pitch. So you get more leeway in the horizontal direction than in the vertical direction. This is the work of the placer. The placer is tasked to that with some other accessory goal, which are minimizing the wire length, the first one. Then, on top of that placement, do not forget that you have the metal wires. Metal wires are used to connect all those cells. The stack of metal wire is usually organized like that. It's not up to scale, of course. So you have metals, metal 1, metal 2, metal 3, metal 4. Between those metals, you can perform some holes, which are called vias. A via is typically defined between two metals, and there is a small quirk, which is that on the last, on the deepest level, it's called the contact, because it goes to the substrate. The substrate is where the transistor lives. So you have contact on the first level, and then vias, just a question of terminology. Those layers are organized in a certain way. In fact, they are alternatively put horizontally and vertically. This way, they define a grid, a gigantic grid, where you put your wire. You don't have, for example, 45-degree wires. You can have them, but not in digital design. Basically, they are all vertical or horizontal, making grid. And at the crossing, you can put, optionally, a contact. A via. So, this is what it gives you. When you have placed your design, then you have to connect your standard cells, and you do so using that grid. Here, the grid has only two layers, the metal 2, which is horizontal, and the metal 3, which is vertical, but you can have more stack of layers. But for the sake of the presentation, I only represented 2. So that's the problem of the routing, and that's too big a problem. In fact, there is too much information. You cannot put that into memory of a computer, of an actual computer. So you have to shrink down the problem. This is where the G cell comes into play. G cells are just groups. That is, you cut down, you make a degraded version of your problems by putting 10 by 10 blocks together. In fact, instead of having all the tracks, I just said I have one node with an edge of 10. This is what is represented here. This is the node, and here we have a 10 capacity. That meaning that I can put 10 wires on that side and 10 wires on that side. And I will solve the routing problem, finding the path between the gates on that global routing grid. And you can see that as we have 10 by 10, the size of the grid is shrunken by a ratio of 100. So I reduce the size of the problem by a 100 factor, which is considerable, and then I can manage it. The computer can manage it. So we start by routing on that big grid, and then we finish the work with the detailed routing. So that explains you the 3-step of making at least 3 steps of making a chip, which are placement, global routing, and finally detailed routing. We will see that in the small demo at the end. So we have other problems to solve, which are, for example, the high-fan-out net synthesis. In a logical equation, what you say is that I have this logical gate, this Boolean equation, which is either 1 or 0, and then I drive any number of things. That is, that value can appear in any other equation anywhere in the chip. But when you make an ASIC, this is not true, because that wire is basically a RC. So you have a load at the end, the capacitance, and the wire is a resistor. So you have delays and you have a drive capacitance, and you cannot drive too many of them. So what you have to do is to break your big wire, unique wire, into a tree of wire. So at any stage, you do not overload the output capacity of the driver, and you keep a sufficiently fast design. Even more complex for the clock tree.
Can we,
the clock tree is...
Can we have,
yes?
Can we place it in 10 minutes? I mean, I know this is a little bit impolite, but...
okay.
Sorry.
So I will skip the chip hierarchy. So the dependency problem, the problem is that when you build algorithm, the algorithms are interdependent. You need to the best implementation is to make them interdependent. One other key point of Coriolis is that it's everything in Python. We write you control Coriolis through complete Python script, and you can intertwine C++ on Python. The high efficiency part are written in C++, and the low part, the slow part, are written in Python. We made some chips, for example, the LibreSoc chip, which is made in TSMC 100 on 80 nanometer. So it's 1.3 million transistors, of which with 800, and you can read the text. I am a bit in a hurry, sorry.
Oh, boo, boo.
So
I
the
mean, that's a
LibreSoc
very
chip,
good project.
it's we are quite proud, and it's partially working in the sense that the teeny thing you can see here is the PLL, and the PLL works, but we weren't able to test the whole chip for a quite stupid problem. That is the design team of the chip wasn't able to provide us test pattern, in fact. So it seems to work, but we don't have test pattern, and we cannot test it extensively. But the PLL works, and the PLL means that the IO pad works, and the standard cell works. We have also made a small VEX RISC-V, this one through the Google program. We don't know if it works yet, because we don't have the chip back yet. And finally, we are also working with a company which is called Pragmatic Semi, which made flexible ICs, and we have made that for them. This chip has been tested functional. It was with a yield of 70%. So it's a small one, but it's on a flexible substrate. The idea is to, for example, for wearable, and it works. So I will go very quickly because I want to make the demonstration. So I will share my transparent later, so you can read it by yourself. But I think the whole interesting point is the demonstration. So I hope you see well my terminal. First, I will clean the directory.
Yeah, we can see your screen.
Okay, so now I did remove the previous run, the result of the previous run. The point, as I said, Coriolis is extensively using Python. So what I use now is a replacement for makefile, which is do it, and you can see the rule in dodo.py. So what you have to write to describe what you want to do with your design, the rule you want to apply, is just write a simple Python file. This is the complete Python file. You see, it's not, you said what you want, and for example, I have the PNR rule here, and you can see it. Okay. We have also a second file, which is the dodesign.py, which describe what you want to do with your design, how to make your design effectively. So the longest part of this design is indicating where the I/O are. So you have some configuration parameter, and that's it. It's mostly copy-paste. Once you have one new design, you can create a new one very quickly. So, first thing first, we will do B2V, which means performing the logical synthesis. B2V is BIF to VST. In fact, we apply Yosys. For those familiar with Yosys in the FPGA, you can recognize its output. And then you get your netlist. Here I have my netlist, which is in VST. VST is in-house. It's a degraded version of VHDL netlist. VST for VHDL structural, which means in fact VHDL netlist. Then I will start in graphical mode and run the script. Sorry, it will go fast if I don't activate the breakpoint. So I will first check that I have the breakpoint activated. Okay, breakpoints are activated. So we can start here. So shift design. Of course, you can do that by programmation. So the first step is to create the clock tree. What you see here is the clock tree. It's a very simple one. There is only one level because it's a small design. And the point is not to making you wait too long. Then we done the high-fan-out net synthesis, and you can see because it's done at netlist level. But now we will perform the placement. Very good. In fact, it's slower because of the transmission. So it's an analytic placer which slowly spread the netlist. That is, it's like a problem with springs. You have load, weight, and spring, and you try to minimize the energy of the whole system. It's a very, the base is a classical algorithm, but the implementation is it's very, very good, very well done. So you see here the structural row, the row of the placement. You can see them. So now we perform the global routing. We are before the global routing. So in order to highlight best the process, I will select one net so you can see exactly what happens. The violet line are the fly line. So you have to say with me. I will select one net. The point is I don't want too big a net. For example, A0. Where is A0? It's too big. A1, A2. Okay, this one is suitable. So A11. No. I said A1. Fit to net. Then I keep it selected so we can see the whole process. A1. And I hide it. So now you see the fly line of one net. That is the global router, then the detailed router have to connect those 3 points. So now we are going to perform the global routing. Here you see the global routing. That is, you have a wire, but which is not very detailed. It goes to the center of the G cells, but you see that it's a progress from the start. And then we will perform the detailed routing. So now I have constructed the first iteration of the detailed routing, and now I will finish it. I will perform the true routing process, which means solving the overlaps, because all those wires will overlap at first. And then you have those little counter which show the decreasing. Okay, that's finished. you have performed the routing, and it says that it's okay. So you can see here, in more detailed way, you have your detailed routing. Okay. And it's finished. Something I didn't have time to show you is that Coriolis is also able to manage analog design. I mean, and not only analog design, but mixed design. That is design containing analog part and digital part. It's actually at the demonstrator stage. It's not fully. It's almost working. And okay, I think I will stop there.
Thank you so much. It's really fascinating to see this, and I think we don't have time for QA because we have Shimizu-san here too. Maybe you do want to stay with us, or you just, maybe you can send us the slides and we can ask you a question offline.
I can send you the slide. Yes. Okay. I will stay online at least for the presentation of Professor Shimizu-san.
Okay.
But I will also send you the slides.
Okay.
And you can ask me questions if you like.
Okay. Thank you.
By email.
Okay.
Okay. So.
Shimizu-san, do you have the? Okay. Oh, okay. You have your own one.